Okay, question 5H2 from the second edition of Statistical Rethinking. Make sure that if you're going to run any of this code, that you have installed and loaded the Rethinking package with these first two code blocks. And okay, so this question revisits the waffle divorce dataset from the chapter and is telling us to assume that the appropriate DAG or causal relationships between M, A, and D, which I believe are marriage rate, median age at marriage, and then divorce rate, I think is what it is. It doesn't matter too much here. But we want to run a counterfactual, and we'll talk about what counterfactuals are, of having the state's marriage rate, or M. Okay? And the book talks about counterfactuals, and so we'll kind of use that as a template, and that all starts on page 140. Okay, so counterfactuals are an idea where we take the parameter estimates of our model, right? So we've ran these models, and we get outputs that look something like this, right? So for the beta coefficient, here's an output, right? This is an estimate of the output. Okay. In a counterfactual, we use those parameter estimates to predict an outcome with different data. Okay, so let me say that again. Our model estimated certain parameter estimates, and these parameters can represent causal effects, right? So beta M or BM here stands for the causal effect of M on the mean value of D. Okay, so hopefully that's familiar to you. And so what we're going to do is we're going to say, well, what if there was different data? What would these parameter estimates predict? Okay, so I think it's maybe worth mentioning that I'm a little bit hesitant to call these things counterfactuals, because in my mind a counterfactual is a world in which we would have had more data or had different data. And if we had that different data, we would have had different parameter estimates. But this is just an aside, just in case. I guess mentioning that hopefully prevents any misunderstanding about what these counterfactuals are doing. Okay, so really they're just predictions with different data given the model that we have. Okay. So one of the things about running these counterfactuals, especially when we have a causal model that is more than just two variables, right, where we have a causal link that goes from M to A to D, right, is that we can no longer use really simple models. Okay, we have to use multiple models. So just let me mention what that means. So in our previous models here, we've been modeling one outcome. Oops, what did I just do? Okay, we've been modeling one outcome variable D, and we've been regressing that outcome on just one or both predictor variables, right? And that was serving our purposes and trying to understand the relationships among the different predictors and D. Okay, but if we're going to run these counterfactuals, we have to embellish that model a little bit, right? We have to represent each of these causal relationships. We have to model A as an outcome of M, and then D as an outcome of A, and all of that has to be wrapped into one model. Okay, so that's what we're going to do here. Okay, so I have my data, and I've kind of standardized my relevant variables as we've been doing for this data set. And so here's my model. Okay, so first I'm going to model the relationship from M to A. Okay, from M to A in our DAG. Okay, and I'm just saying, well, that the value of A, or the mean value of A, is a function of some average value, some intercept, as well as the causal input from M, and I'm calling that M, and then I'm using the beta MA, so M affecting A. That's the nomenclature I'm adopting here. And then similarly, we have to model D, and D, according to our DAG, is just a function of A, right? So we have D, and now I have its regression, and it is its own intercept, as well as the causal input of A onto D. right? And that's all. So I'm going to run this model, and we get outputs here for each of our coefficients, right? These are our parameter estimates. I should say parameter more than coefficients. Coefficients are a class of parameter, right? So anyway, so we have our different parameters here, estimates for our parameters, okay? And we're not going to do it here, but if you were to go through these, you would find that we're making very similar predictions from what we found in earlier models, right? So namely, in our earlier models, we found a negative association between M and A, right? And that's what we have here. We found negative associations between A and D, okay? And we also found positive relationships between M and D. So how do we get a positive relationship out of all of this? Well, so we have two beta coefficients here, one representing from M to A and then one from A to D. So if I multiply BAD and BMA, or maybe I should go in the correct order, this coefficient representing the M to A relationship and then the A to D, we would get a value, but notice that it's that they're both negative, and so the result is going to be positive, therefore positive association between M and D. Okay. Anyway, you can do that on your own time, but just making some connections to what we've done so far. Because now we need to build our counterfactual models, and the book describes 3 generic steps to building our counterfactuals, and so I'm going to show that in the code here. Okay. So the first step is to pick a variable we want to manipulate. Now the variable that we want to manipulate is M, right? We are, according to the question, we are halving or cutting in half the state's marriage rate, M. Okay, so that's what we're going to do, and then we're going to pick a range of values for M. Okay, and so I'm just calling that M sequence because I'm just gonna run a sequence from -3 standard deviations, which should cover 99% of the possible M values, to +3 standard deviations, right? So that range should cover, the 3 standard deviations on either side of the average. And then I'm just saying, give me 100 evenly spaced values between -3 and 3. Okay. And now I'm going to simulate these values, okay, according to the model M. So I use the sim function, which is part of the Rethinking package. I'm simulating average values from M, okay, I'm going to use, I'm going to use as part of my data, instead of using M, I'm going to use mseek, right? So instead of the actual values of M, I'm going to use mseek. Okay, and let me just run that. And what I get out are outcomes for A and D, right? So I get 1,000 predictions over the 1 through 100 values for M, right? So every value of M, I'm getting 1,000 values, or 1,000 predictions. Okay. I want to plot this to make it kind of easy to see. So I'm going to have 2 graphs right next to each other. So I'm going to calculate the means of A. So for each one of these, so for each value of M, what is the average value of the 1,000 predictions for A? Okay, so I'm just taking call means of this right here, that matrix there. Okay, and similarly for D. And then I'm going to apply the HPDIs, the high probability density intervals for A. Okay, and this is the code to do that, as well as for D. And now I'm just going to plot it as well. So I'm going to plot the mean values here, the mean values of A across the different values of M, as well as the HPDI, and then the values of D for each value of M. Okay, so now remember, M is affecting D through A, and so the second plot will represent kind of the whole chain here. All right. So what we have here are counterfactual values. So we have A and D on the y-axis, and then M on both x-axes. All right. And so the solid line represents the mean prediction of A for each of these values of M. Okay, and then the light gray is the HPDI. Okay, so these are our counterfactual models, and so we can say, well, had M been one standard deviation above the mean, then A would be, roughly a little bit greater than -1, and D would have been a little bit greater than 0. Okay, in terms of standardized units. Okay. But we probably want, well, okay, so we're not done yet, because now we need to determine the effect of cutting in half the average marriage rate. So the first thing we need to do is figure out what the average marriage rate was, okay, what half of that is, and then what that value is expressed as a standardized unit. Okay, and so you can kind of walk through all of the math there. This last one is the only thing that might be a little bit tricky, but remember, when we're standardizing a variable, generally what we're doing is we're taking the value minus the mean of those values divided by the standard deviation of that value. And so the value that we're using here is half of the marriage rate. Okay, so so we get this in standardized units, right? So in other words, if I were to go here on my x-axis for M, it is the difference between being here, right, because that's the average value for M, and then looking at the effect of making the average value -2.6, so pushing M way over here to the left. Okay, so we need to figure out then what is D going to be, or the average value of D, and so we should be able to get an estimate. It's going to be around -1. It looks like if I just go up. Okay, so let's do that. So so we have our standardized new value for the mean value of M. Okay, and so I am going to simulate data once again, just like I have above, and I'm going to calculate the difference between, okay, so my new data is 0, right, when M is its average, versus its new average, which is half of the previous average. So so I'm going to run the simulation again on that new data, and I'm going to get predictions again for A and D, and I'm then for each one of those predictions for D, I'm just going to take the second. I'm going to take the second time point, which corresponds to half A, or half M, minus what it was initially, right, which is the average M. Okay, so I run all that, and then I'm going to plot it. Okay, all right. So it says then that the effect of having cutting in half the marriage rate would be about a -1 standard deviation. It would be a -1 standard deviation reduction in divorce rate, right? And so I've kind of plotted that right here, right? So here's the new M value, and then the predicted D value. Okay, and so in terms of real units of divorce, you can just run this code. So we're going to reduce divorce rate by about 1 standard deviation. So I have standard deviation of divorce rate times the predicted reduction, and so that means that divorce rate would go down by about 1.9% or so. Okay, okay, that's it.